to the 5th lecture in the 7th week of our course Analysis of a Complex Kind. In today's lecture, I'll show you a number of examples that demonstrate how the residue theorem can be used to evaluate complex integrals. Let me start by reminding you of the residue theorem. Suppose D is a simply connected domain and F is analytic in D, with the exception of isolated singularities. I've denoted those isolated singularities with little crosses below. Suppose furthermore that C is a simple closed curve in D that doesn't pass through any of the singularities of F. And let Z1 through Zn be those singularities of F that are surrounded by C. Then the integral of F over the curve C can be found as 2 pi I times the sum of the residues at those points that are surrounded by C. Let's look at an example. Suppose we wanted to find the integral of the function e to the 3 over z over the circle of radius 1 centered at the origin. Where does the function f have singularities? E to the 3 over z is undefined when z is equal to 0 because we would be dividing by 0 at that point, but it's actually analytic everywhere else. So we have an isolated singularity at 0, and it turns out that isolated singularity is an essential singularity. The integral can therefore be found by the residue theorem as 2 pi I times the residue of f at 0. How do we find that residue? First, we remember that the exponential function has a Taylor series representation centered at the origin as 1 plus w squared over 2 factorial and so forth. If we write that in summation notation, that is the sum k from 0 to infinity of 1 over k factorial times w to the k. Now we want to find a Laurent series expansion for e to the 3 over z so that we can find the residue of e to the 3 over z at the origin. Because 0 is an essential singularity for the function f, we can't use any of the tricks we learned last class. Rather, we actually have to find the Laurent series expansion. But that's now easy, because we simply plug in 3 over z for w. We find that e to the 3 over z is the sum 1 over k factorial times 3 over z to the k. In order to find the residue of this function at 0, we need to find the 1 over z term. What does 1 over z get multiplied with? Well, we get a 1 over z exactly when this k is equal to 1. When that k is equal to 1, we have a 1 over 1 factorial and the 3 from the numerator. That must be my a negative 1 term. So therefore, the residue, which is a negative 1, is equal to 3. And that means that the integral that we're interested in, the integral of the function e to the 3 over z integrated over the circle of radius 1, is equal to 3 times 2 pi I, and that equals 6 pi I. Here's another example. Suppose we wanted to integrate the function tangent z over the circle of radius 2. Where are the isolated singularities of the tangent function? Tangent z is sine z over cosine z, which is analytic everywhere except for cosine z is equal to 0. But cosine z is equal to 0 at pi over 2, negative pi over 2, 3 pi over 2, negative 3 pi over 2, and so forth. Those singularities that are surrounded by the circle of radius 2 are at pi over 2 and negative pi over 2. In order to evaluate the integral, I therefore need to find the residue of the tangent function at pi over 2 and then negative pi over 2. I need to add those two residues up and multiply the result by 2 pi I. How do we find the residue of f at pi over 2? We notice that f is of the form an analytic function divided by another analytic function, sine z and cosine z. And those two analytic functions satisfy that the denominator function is equal to 0 and has a simple 0 at pi over 2. By the theorem that we ended with in last class, we remember that we can find the residue of f at pi over 2 by simply taking the numerator function, evaluating it at pi over 2, and dividing it by the derivative of the denominator at pi over 2. The numerator is sine z, so we need to find sine of pi over 2. The denominator is cosine z. Its derivative is negative sine z. At pi over 2, that gets us negative sine of pi over 2. Sine of pi over 2 is 1. Negative sine of pi over 2 is negative 1. The quotient evaluates to negative 1. And therefore, the residue of f at pi over 2 equals negative 1. Similarly, the residue of f at negative pi over 2 is the numerator at negative pi over 2 divided by the derivative of the denominator at negative pi over 2, because the denominator function cosine z again has a simple 0 at negative pi over 2. Therefore, we can evaluate g of negative pi over 2, which is sine of negative pi over 2, divide that by the derivative of the denominator, negative sine of negative pi over 2, and we find ourselves with negative 1, which is sine of negative pi over 2, and negative 1, which evaluates altogether to a quotient of negative 1. Both residues are actually equal to negative 1, so that the integral of tangent c dz over the circle of radius 2 evaluates to 2 pi I times negative 1 plus negative 1, which equals negative 4 pi I. Here's a third example. This is a function we've looked at before. F of z equals 1 over z minus 1 squared z minus 3. This function has isolated singularities at z equals 1 and z equals 3. I drew two curves here, a curve C1 that surrounds only the singularity at 1, and a curve C2 that surrounds both of these isolated singularities. We'll find both integrals. First, we'll start with the integral over the curve C1, which by the residue theorem is 2 pi I times the residue of f at 1. To find the residue of f at 1, I notice that at 1 the function has a double pole. To find the residue at the double pole, I simply multiply the function by z minus the double pole squared, and then take the derivative, and then the limit as z approaches the pole. That's the formula we developed last class. Conveniently, we notice that z minus 1 squared in the numerator and z minus 1 squared in the denominator cancel out, so that we're left with having to find the derivative of 1 over z minus 3, and then the limit as z approaches 1. But the derivative of 1 over z minus 3 is negative 1 over z minus 3 squared. When we take the limit as z approaches 1, we can simply replace this z with a 1. 1 minus 3 equals negative 2. We square that, we get 4. So the residue is equal to negative 1/4. Therefore, the integral of my function over the curve C1 is 2 pi I times negative 1/4, and that evaluates to negative pi I over 2. Next, let's look at the other curve, the curve C2. This time we need to find the residue of f at 1 and the residue of f at 3 and add the two things up. We already found the residue of f at 1, and that is equal to negative 1/4. Now we need to find the residue of f at 3. We notice that the function has a simple pole at 3, therefore we multiply by z minus 3, and then take the limit as z approaches 3. No need to take a derivative for a simple pole. We notice the z minus 3 term cancels out conveniently, and we're left with having to find the limit as z approaches 3 of 1 over z minus 1 squared. To find that limit, we simply replace z with 3. 3 minus 1 is 2, 2 squared is 4. The residue turns out to be 1/4. Now we notice when we add those two residues, negative 1/4 plus 1/4 adds up to 0. So the integral comes out to being 0 when we integrate over the curve C2. So far, all the integrals we evaluated were integrals in the complex plane. The residue theorem can actually also be used to evaluate real integrals. For example, of the following forms. An integral of a rational function of cosine t and sine t. Here you see a rational function of x and y. Both numerator and denominator are polynomials in x and y. When I replace x and y by cosine t and sine t, I find that r of cosine t and sine t equals cosine squared t minus sine squared t over 1 minus cosine t plus 1/4, and we can actually find this integral using the residue theorem. And it turns out this integral equals pi over 3. Other examples are integrals of rational functions, integrals of a rational function times a cosine of alpha x, integral of a rational function times sine of alpha x. In the next and last lecture, I will demonstrate for you how to find an integral of this last type. I will evaluate an integral from minus infinity to infinity of a rational function times cosine of alpha x.